The following case study is an example of how engineered residual compression successfully mitigates foreign object damage in gas turbines. This study focuses on titanium vanes in the Harrier fleet. The U.S. Marine Corps' AV-8B Harrier jets are powered by F402 Rolls-Royce 408 engines. The first-stage low-pressure compressor vanes in these engines were prone to failure from cracks in the inboard trailing edge of the airfoil near the platform. Several Class A mishaps involving the loss of pilots and aircraft have been attributed to fatigue failure of this vane. The vanes were found to have an extremely low foreign object damage or FOD tolerance, posing an ongoing safety concern for the fleet. Previous attempts at prevention included frequent inspections and regular vane replacement. While technically successful, this impacted fleet readiness and increased maintenance costs. The limited availability of F402 replacement parts threatened eventual grounding of the fleet. At Lambda, we use designed compression to mitigate foreign object damage and extend component life. Introducing a layer of compressive residual stress deep enough to contain surface flaws from FOD mitigates cracking without having to alter either the component material or design. This can be performed through manufacturing processes such as shot peening, laser shock peening, deep rolling, and low plasticity burnishing. The depth, magnitude, and distribution of the residual compression are designed specifically for each component and application to produce optimal performance. This means going through a process to calculate the minimum residual stress required to mitigate fatigue cracking from FOD. We do this using our proprietary fatigue design diagram. Within the triangular region marked safe, the FOD-prone region is in a fully compressed state throughout the cyclic loading seen in service. In the absence of tensile stresses, cracks cannot initiate or propagate. In the F402 vane example, it was determined that introducing a minimum of -100 ksi or -690 MPa would restore nominal fatigue strength to the damaged surface. Once the engineered residual stress field is designed, the vanes are processed. We use low plasticity burnishing to introduce designed compression. LPB has several benefits over other processes, such as minimal cold work, which makes the compressive layer more stable at elevated temperatures. LPB also leaves a smooth, mirror-like surface finish on all processed parts, which facilitates inspections and improves efficiency of airfoils. Component-level fatigue testing verified that LPB treatment completely mitigates 20,000th inch or 0.5 millimeter deep FOD and restores fatigue properties of both test coupons and actual LPC1 vanes removed from service. Following laboratory component testing, LPB was applied to vanes for engine testing. ASMET engine testing by the OEM proved that LPB resulted in complete mitigation up to 25,000th inch or 0.63 millimeter deep FOD introduced by ballistic impact at the trailing edge failure location. This was reported to be the first time deliberately damaged airfoils were ever subjected to an engine test because of the risk of complete engine failure. LPB produced through thickness compression in the critical vane edge, completely inhibiting crack propagation. After receiving the successful engine test results, NAVAIR approved LPB for improving the damage tolerance of both new and in-service LPC1 vanes. Over 16,000 in-service LPC1 vanes have been LPB treated and installed in the F402 Rolls-Royce 408 engines over the last decade. The improved damage tolerance has eliminated a major flight safety issue threatening continued operation of the Harrier fleet and provided substantial cost savings to the U.S. Marines. Ease of implementation into existing manufacturing and maintenance procedures has made LPB a very cost-effective means of improving the damage tolerance and extending the service life of these critical flight components. To learn how engineered residual compression can extend the life of your component, visit our website at www.lambdatex.com.